Hello, everyone. I hope you enjoyed the symposium. It's one of the last talks. My mentee, Damla, is a physicist from Boğaziçi University. We studied on the restricted three-body problem in a sense that none of the, well, not none, but most of the mathematicians do not study. She's going to talk about on that. Well, stage is yours, Damla.
For introducing me to his little group. Today we'll talk about restricted three-body problem. The outline is as follows. First, I will talk about a little bit history of the three-body problem, and then we're gonna study the equations of motion of the three-body problem. And following that, we will give the energy surface and equilibrium points. And finally, differential correction will be studied and the recent studies will be given. Okay, the history of the three-body problem actually goes back to Newton and Kepler, or n equals 2, the two-body problem, actually. Newton just studied the equations of motion, and then Kepler just introduced the orbital mechanics and the orbits of the celestial bodies. And then people tend to ask that, what if we increase the number of the bodies? And the three-body problem arises. Poincare is the key figures of the three-body problem, actually. And he introduced the chaotic nature of the three-body problem and said that these problems can be solved precisely, just as in the Newtonian mechanics. Actually, we're going to study the very specific version of the three-body problem, which is restricted three-body problem. And in this configuration, we have two big masses, and the mass of the third body is so little that we will ignore its mass and the effect of the forces and the energy. So we're going to study in the rotating frame. We actually study in the inertial frame in classical mechanics, but this time will be different. We will be in the rotating frame because it's a lot more easier to calculate in rotating frame. Why? Because when you rotate the plane, you rotate these masses, and the kinetic energy of these masses will be equal to 0. So you can calculate even more easier when you take the kinetic energy of these two is equal to 0. So the lowercase x, y, and z are my coordinates in the inertial frame, and the capital X, Y, and Z are the coordinates in the rotating frame. So we're going to apply the rotation matrix to the system just to get the rotating frame coordinates. Okay. These are position vectors. So I'm going to go to velocity vector. So I'm going to differentiate it with respect to time. So this is going to be my coordinate of the rotating frame in the inertial frame. Okay. Now that we know the velocities, we can calculate the kinetic energy and the potential energy. And the potential energy in the system will be due to the gravitational forces. Remember that we're going to study planar, circular, restricted three-body problem. Planar means we're going to take xy plane and take z is equal to 0. So it only depends on the xy and x dot, y dot. In the potential energy, we will have such a parameter called mu, mass parameter, and our phase space just depends on the mass parameter, which is equal to m2 over m1 plus m2. I mean, you can change the system just changing the value of the mu. I mean, if you want to study the Jupiter and Sun system, you can give a value to mu. And if you want to change the system to Earth-Moon system, you can change the mu value, and then you can evaluate all the system and the system's trajectory and so on. And here R1 and R2 is the distance between them. Now we will define Lagrangian of the system. We will study the Lagrangian mechanics rather than the Newtonian mechanics. And Lagrangian is defined as follows. You can see here the kinetic term minus the potential term. In our system, it is equal to the equation 5. And we're going to define Euler Lagrange equation and plug the Lagrangian into this equation so that you can get the equations of motion. These are my equations of motion. And U bar is equal to effective potential energy. And it is defined as such. It's defined as so. This is potential energy, and this is the minus 1/2 x squared plus y squared. This is actually the energy due to the centrifugal force. I subtract this term because I cannot make work on this. Okay. Now I will give some definitions regarding the evolution of the motion. Jacobi integral is the constraint of the system and depends on the energy, and it is equal to -2 times energy. And you can derive the Jacobi integral using the energy function and equations of motion. We will plug this energy into Euler Lagrange equation, and you're going to get this constant. And after some point, you will get something like is equal to 0, which means Jacobi integral is actually a constant. The energy surface or energy manifold. This is actually the inverse image of the energy function. And when you fix the energy, you can talk about the manifold and energy surface. Fields region is actually the projection of the energy surface onto position space. And it tells us about the allowed regions and forbidden regions. And the boundaries of the Hill region is called zero velocity curves. And the particle is at rest at that point. So the potential energy is at maximum. Now we will study the location of the equilibrium points. There are two cases when we study the location of the equilibrium points. This is the first case, equilateral points. In this case, we will study in the xy plane, so y will not be equal to 0. For the sake of simplicity, I will change the variables. I will define my u bar instead of R1 and R2 in terms of R1 and R2 instead of X and Y, just for the simplicity. And when we study the equilibrium points, you gotta take the derivative of the effective potential energy with respect to your variables. And I will take the derivative with respect to R1 and R2 so that I can find R1 and R2 values. So we know that the x coordinates of the equilibrium points must align with the center of mass. So I know what the x value is. And I will plug the x value into this equation so that I can get the y values. And y value is that. Now we have 2 points. We have to find 3 more points. And these points called collinear points. In this case, we will take y equals 0. And when you plug the y equals 0, you will write down the effective potential energy function again. And this is what it is. I'm not going to delve into the solution because it requires a little bit of serious solution. I will just tell you that there are 3 intervals here. So I have to get 3 critical points. That's all that you need when you study the location of the equilibrium points. This is the most important part, I think, in terms of mathematics of the 3-body problem. You have a second order differential equation and you want to solve it so that you can get the trajectories of the celestial bodies. And so you have to linearize the whole system. First, we will use Hamiltonian approach, and then we will use inverse Legendre transformation to get the Lagrangian approach. I will define my Hamiltonian as in the equation 19. And these are my equations of motion, defined as follows. To linearize the whole system, I will use inverse Legendre transformation and use this definition. I plug this into some other equations, and then you will get those equations. Now I have linearized my system, so I can use linear algebra. I have found my eigenvalues and corresponding eigenvectors. Eigenvectors carries the information of the stability and whether the motion is periodic or not. It is important in that part. So, for instance, look at case 3. I will define my position vector. This is my velocity. This will define a circular motion. This means periodic orbit or Lyapunov orbit, whatever you call. Now I will transform my coordinates just for the simplicity again. And here you can see Jordan canonical form here, I will use. And now my system is in the form of this equation. And those equations comes from this identity actually. And you gotta notice that eta c and zeta 1 squared and plus zeta 2 squared will be my constants of motion. When you take the derivative with respect to time, actually, you plug it into a Lagrange equation again, you will get 0 because it's constant. And I will define my energy function again in terms of constants of motion, and I will evaluate this function geometrically. I call this part, I make this equal to r squared. So this will give me a circle whose radius is r. And this will give me this solution. And those are my forbidden regions because my energy doesn't allow me to go through that. Okay. It's more like an engineering problem because the motivation is actually that you try to fit the trajectory into Lyapunov orbit, which is periodic orbit. So you want something like this. And I will call my trajectories phi flow. And this is the second flow. This is my initial condition, and this is the perturbed condition. And this is the distance between them. Um, I will say that T is equal to T1. I write this as follows. And then I will tailor expand this equation, and this part will be my state transition matrix, which helps me to evaluate and apply the differential correction. And unless you find the state transition matrix, you can apply the differential correction. The motivation is actually when you perturb your system a little bit, you want your system to be approached a little bit to the Newtonov orbits. Initial condition, my perturbed condition, and the distance between them. Recent studies on three-body problem. This is actually a well-studied problem even today. There's something called mass transfer, electromagnetic two-body problem, space mission design, and Moser regularization. And mass transfer is all about you have two suns, and one of the sun just attract the other sun's atmosphere so that it will gain some mass and it'll lose some mass. So the problem is how the spacecraft or satellite or whatever you use will move between them. I really want to talk about Moser regularization because it's an important part of this problem. It's actually about the collisions. We have something called collisions. It is like the body, any two of the bodies cannot be in the same position at the same time. So it is called collision, okay? And we don't want it. So we extract this part from the manifold. So I have a hole in the system. So how will I cope with this problem? And this is where the Moser regularization begins. And it is something like this. It's a beautiful simulation. At the same position, and then reflects it. We have a surface here, and the third body comes, hits, and reflects. Okay. Those are the references. If you are interested in this problem, you can delve into the references. If you have any questions, I can